Okay. So in yesterday's lecture, we were talking about some additional operations on fuzzy sets. Let us revise those operations first before we move ahead with today's lecture. So what are those operations? The additional operations that we discussed yesterday.
Algebraic sum, algebraic product.
Right. So
Bounded sum,
algebraic product. What is the formula for this?
bounded sum,
Bounded sum and bounded difference, right? So what is the formula for this? What is the formula for algebraic sum?
um, it's uh, it's fuzzy set A plus fuzzy set B, like no wait, the membership value of A plus the
Hmm,
membership value of B minus the product of the two,
correct. What about this?
just the product of the two membership values.
Right. What about bounded sum?
It's the minimum. It's like the min of the sum of the two membership values and one.
Right.
And
Similarly,
bounded difference is the max of is zero, and the difference between the two membership values. Oh wait, sorry, my bad.
yeah. So these were the different operations. Apart from this, two more operations we have missed out. One is, which is that operation which converts a 1D fuzzy set to a 2D fuzzy set?
Cartesian product.
Yes, yes, yes. So that is Cartesian product. And what is that? Which operation do you perform? Actually, you are considering the elements of set A, fuzzy set A and B pairwise, right? Considering the elements of fuzzy set A and B pairwise. And for each pair of these elements, you are writing out the membership here, right? What is the membership? It's the min. It's the min of the two values, right? So A is some element XA is having some membership in set A, and XB is having some membership in set B. So the membership of this pair of elements in the Cartesian product of A and B is the minimum of the membership values in these sets, right? Remember or no? This is the min value. The min membership value of these two elements is put here. Okay. So this is Cartesian product. So likewise, you can extend this if you want to combine n different fuzzy sets. N different fuzzy sets. So if you want to combine n different 1D fuzzy sets into together, you can use Cartesian product. Okay, and you will have an n-dimensional relation, an n-dimensional fuzzy relation. Okay. Apart from this, the last operation that we had studied was, which is that?
Exponential.
The power of a fuzzy set, right? So what is the power of a fuzzy set? Whatever is the membership value, you raise to that value, P. Okay. I say I want to compute A raised to P. So whatever this power P, the individual membership values of that element, those all the elements in set A have to be raised to this power. So if this power is 2, all memberships will be raised to 2. If it is 4, everything will be raised to 4, and so on. There is power of a fuzzy set, right? So these were the additional operations that we talked about in the last lecture. Anything missed out?
No, ma'am.
Okay, let's move ahead. So today we'll be looking at 2 more operations, that is concentration and dilation. So concentration and dilation performed on fuzzy sets. We'll be solving a problem. We're looking at a problem based on these operations. We'll look at some more terminologies, and we will also look at standard fuzzy membership functions. So this is the outline for today. So let's start with the first topic, that is concentration and dilation. Okay. What do you understand by concentration and dilation? So if A is a linguistic value, okay, so these operations actually are with respect to linguistic values. And what are linguistic values? Linguistic values are nothing but they are fuzzy sets, right? So for example, if age is a linguistic variable, if age is a linguistic variable, the values are young, middle-aged, and old. These are the linguistic values. Words which are taken from natural language, okay, which describe this variable are nothing but linguistic values. Okay. Now, what is important to note here is each of these linguistic values in turn are nothing but fuzzy sets. So I say young. Young is a linguistic value, but with that value, I design a fuzzy set called young. Right? Middle aged is a fuzzy set. It is also a linguistic value for the linguistic variable age. Right? So now let us again switch back to the definition of concentration and dilation. So if A is a linguistic value, then the operation concentration is defined by con of A notation is equal to A square. Okay. So when you say con of A is equal to A square, and dilation is defined by dil of A is equal to A raised to 0.5. Okay. So what is this? What is the meaning of this? What is this? Raised to something. Which operation is this? This is power of a fuzzy set, right? So these operations actually, concentration and dilation, they are defined using power of a fuzzy set. Okay. And the standard power that is used for finding out concentration is square and dilation is half, 0.5. Okay. So what does that mean? When I perform an operation concentration on the fuzzy set, I raise each element's membership to half or to 2, right? I square it. I square the membership of each element. Okay. And that is what the set that I get is nothing but concentration of A. And if on the other hand, if I am raising the elements membership to half, then that set which I'm getting is dilation of A. Okay. So since these operations are there, what is the use? What is actually the use of performing these operations? Let us look at that. Suppose I want to define this set called more or less tall. So I have a set called tall with me. I have a set. Just assume that I have a fuzzy set called tall with me. Okay. And using this fuzzy set, I want to define this particular fuzzy set, more or less tall. Okay. Then I can use the operation dilation of tall to define more or less tall. Okay. So using these operations of concentration and dilation, actually you can use an existing fuzzy set to define other fuzzy sets based around that very idea. Okay. So how will you define very tall? Assuming that you have tall with you, you will make use of concentration. You will make use of concentration. Now, why do I use dilation for defining more or less tall, and why do I use concentration for very tall? What do you think is the reason?
Concentration increases the value.
Concentration increases the value. Which values of the membership? Okay. Yes, of the value, the membership values, it increases. Now, in case of squaring a value, if the membership value is low, if it is low, like for example, a membership value is 0.1 in a particular fuzzy set. Okay. Then what will happen to that value if I square it? What will happen to the value? Will it increase or decrease?
Decrease.
Decrease.
Okay. So actually what is concentration doing? Concentration will reduce the membership values, and the smaller the membership value is, the reduction is more. Right? So if I have to go from a fuzzy set tall to very tall, then in that case, the membership values which were high in case of tall will reduce, right? In very tall. And which were very low will become still low. Which were close to zero, they'll become still low. They should. Intuitively, they should. Yes or no? If I'm designing, I have a set of tall people, right? I have a set of tall people. Suppose I start giving membership values from, say, 5 feet. 5 is given 0.1. So when I'm going from fuzzy set tall to very tall, then what should happen? This particular element should get an even lower membership in very tall. Correct? Are you getting it? Okay. So if what this concentration operation does is, if the membership is less, if the membership is small, it will reduce it further. Okay. On the other hand, if it is closer to 1, so it's very close, it will still reduce it, because 0.9, suppose it is 0.9. What is 0.9 square? It is 0.81. It will still reduce it. But that impact will not be that much, right? So as you're moving from one tall fuzzy set to, higher values in that domain, then this concentration operation is going to help you. So if you want to move from tall to very tall, you have to go for concentration, but understand what is happening to the membership values. You are actually getting closer to the intuitive definition of that fuzzy set. Okay. Now you tell me what will happen in case of dilation. Dilation is 0.1 raised to half. So suppose in my set tall, I have this 5 with 0.1. What will happen when I raise it to half? What is 0.1 raised to half? Can someone tell me?
1.01.
Exact answer. Compute. Tell me. It's increasing or decreasing?
Point 316.
Increasing.
0.316. Okay. So dilation. So what you're doing is you're going from tall to more or less tall. So what will happen? That 5 feet tall person will get a slightly higher membership. Yes or no? It will increase. It will increase in that set, more or less tall. Okay. So as you're going from uh, one set to the other set, from tall to more or less tall, or from tall to very tall, you have to use either dilation or concentration. Okay. And what is the effect of concentration? Concentration reduces the membership of elements having small membership values. Okay. Concentration reduces the membership of elements having small membership values. And dilation increases the membership of elements having small membership values. This is very important. Is this statement clear? Are the statements clear to you? What is happening and how it is working correctly? Example, the same example. So if this is tall, if this fuzzy set is tall, whatever is written here, then, right? So it's like 5, 6. I mean, we have just written some arbitrary heights here. 5, 6, 6.5, 7, 7.58. Okay? And see, the membership is increasing. Are you getting it? Very tall is concentration of tall. Very tall is concentration of tall. That is tall raised to 2. Okay, the membership raised to 2. So what has happened to this? It has become, this 0.125 has become 0.0165. It has reduced. Yes or no? It's reducing. And here it is not making much of a difference. Here it is not making much of a difference. These values are high membership values. They are 1. Okay. Here it has reduced. 0.875 has reduced to 0.76. Okay, for this person. 6.5. I say very tall will be 7, 7.58. That is 1. Okay. So that is very tall. Now, more or less tall. More or less tall will be tall raised to 0.5. So when you look at it, this has increased. This has increased. Phi has increased. Right? It is increasing. Okay. So you have to see that for concentration with small membership values, they are reduced further. And when you use dilation, the small membership values, they are increased. Okay? That is important. Now, with this definition, let us solve this problem. Okay. So this example will make it more clear how to use it. Okay. So low temperature, high pressure. These are the 3 fuzzy sets which are given to us. Okay. The temperature ranges are 131 to 139 all throughout. Steps of 1. So there is no middle ground there. 131, 132. Okay. That is the precision of measuring the temperature. Similarly, the pressure limit is 400 to 1000. Okay. And again, the steps are discrete in nature, 100 by 100. Right. So what you have to do here, you have to find the membership functions. Temperature not very low, temperature not very high, pressure slightly high, and pressure very, very high. So what is given to you? Existing fuzzy sets. And you have to use these operations of concentration and dilation to your advantage and compute these new membership functions. Okay. So one by one, let us try to solve. So temperature is not very low. What is temperature not very low? How will you create this fuzzy set temperature not very low? Using this low temperature is given to you. Okay. Can you compute very low using this? Low temperature is given to you, right? From low, you can compute very low. And from very low, can you compute not very low? Yes or no?
Yes.
What will that be? It will be 1 minus very low. Not very low is going to be 1 minus very low. 1 minus very low means the membership values. We are talking in terms of only the membership values. Okay. And how do I go from low to very low? Which operation do I perform? Should I perform concentration or dilation?
Concentration.
Concentration. You sure?
Yes.
Okay. So concentration, if I perform, I'll get very low, and then I'll take the complement of very low, so I'll get not very low. That is what I'm going to do. So let us solve it. So this very low is nothing but concentration of low. And what is it? Low raised to what? Low raised to
2.
2. So 1 square, right? Correct? These are the values. Sorry, 0.616. Right? 135. Okay. Now, what is not very low?
1 minus.
1 minus very low. Right?
Yes, ma'am.
What else? You can consider the universe. You have to consider the universe. Universe is 131 to 139. Okay. Next is very high. What is very high?
Concentration high.
It is making sense now intuitively. Observe
Yes.
the values. Yeah. Concentration of high. Actually, you have to compute not very high. So we are going stepwise, right? Temperature not very high is the second question. Okay. So very high is concentration high is square it simply, right? I suggest you should solve this along if you're looking at watching the lecture, because that will help you. Otherwise, you will not have a habit of solving things. 0.36, and not very high will be following that. Okay, so not very high will be 1 minus very high, which is the same as the previous thing. Fine. So not very high will be 1 by 131 plus 1 by 132 plus 1 by 133, right? 0.96 by 135. 0.64, 0.36, and it will decrease. Okay. Now, what is slightly high?
Dilation.
Dilation. So that is dilation of high. Dilation of high is high raised to 0.5. Okay. So now you will have to compute this. I'll leave this for you. Okay, compute it. Raised to 0.5. High raised to 0.5, you have to find. Fine. What is very, very high?
Concentration very high.
Concentration of very high. So using this fuzzy set, you can find. And if you were not asked to compute this, it will be concentration of high. Correct?
Yes.
Okay. So twice you have to raise it. So it's basically high raised to
4.
4. Is this clear? Okay. So, but it is the pressure. Huh? The other question is the pressure. That was a temperature. So that very high, actually, these values, whatever we were computing, these were temperature values. Remember that. Just look at the question before you attempt solve it, because then this is the pressure. Sorry, this is the pressure. Slightly high, and this was the pressure. The question, right? The first
Yes.
two questions are for the temperature, next two for the pressure. Yeah. Okay. So let us move on with more terminology. So this is some more terminology that we are interested in when we talk about fuzzy sets. Okay. First one is crossover points. Okay, we will look at each of these one by one. So first one is crossover points. So crossover points, basically, it's a point at which x is equal to, okay, there's a typo here, mu of x. Mu x is equal to 0.5, right? Crossover point of a fuzzy set is the point where the membership is 0.5. Okay, so at what point actually it crosses over? So if it is this kind of a function which is there are two crossover points, this and this. Okay, so what is shown in this diagram is the point where the membership is 0.5, exactly that particular point is called a crossover point. Now this definition actually comes in the context of fuzzy sets when you're looking at continuous ranges. That is important, because you're looking at a continuous range of values. You're looking at a continuous range of values, and at that point where there is a it goes from one, I mean, there's a crossover, sort of a crossover. It is crossing this 0.5 threshold, so that is known as a crossover point. Okay. This particular function has two crossover points, because it's what's happening is at this stage it is crossing over from zero point 0.5 to 1, and at this stage it is coming back from 1, and it's dropping actually, and it is moving towards 0. So this is also a crossover point. Okay, so some other function, if it is something like this, okay, this is 1, say, so there'll be only a single crossover point, because this function is just an increasing function. On the other hand, this is a closed function. Okay, so that is why there are two crossover points. Next, convexity. So a fuzzy set is said to be convex if for any x1 and x2 which belongs to x, any lambda that belongs to this closed interval 0 and 1, this relation holds. Okay, this relation holds. What is the relation? The membership of lambda x1 plus 1 minus lambda x2 should be greater than or equal to the minimum of the two memberships, x1 and x2. Okay, so if you consider any pair of points x1 and x2 inside x in this domain, in the universe, okay, then this particular relationship, the membership of this point, lambda x1 plus 1 minus lambda x2 should be greater than or equal to the minimum of these two values. Okay, what is the meaning of this? What is the meaning of this? If you have some membership function like this, okay, this particular membership function, let me draw it. Okay, I'm drawing it. If I consider any point, okay, that particular point, I mean, if I look at this, let me look at this from the shape of this function. So if this function, what happens is this function is increasing after this point, right? It's increasing, and here it has become constant. Then again it increases. Okay. So if it decreases, then in that case it should not increase again. Okay, should not increase again. So you cannot have something like this and you can call it convex. So if I have something like this, okay, if it is decreasing, then it should not increase again. Okay, in other words, if a fuzzy set is having dips, if there is a dip, then it cannot increase. If it increases, like if the shape is somewhat like this, if there's a dip and there's a sudden increase, and then again it is decreasing, then this is non-convex. This particular fuzzy set is non-convex. Okay. On the other hand, this particular set is convex, because what happens is if it decreases, if it increases, it will increase. Fine, it is increasing. If it decreases, it is not again increasing, and then it is going down. ऐसे होता है तो it is not convex. But after this point, it is decreasing only. So if there are dips like that in the structure of the membership function, then it is non-convex. Okay. So what about this? What about this? This particular membership function. Is it convex or non-convex? If there's a
It's
dip, it's convex. If it is decreasing, then after this point, it has to decrease only. Whenever it is decreasing, it has to decrease. After decreasing, when it decreases, now it can increase. It can increase. This is fine. Okay. But if it is decreasing at some point, then after that point, It has to decrease only. The moment there's a slight increase here, then it becomes non-convex. Okay, and that has to do with this. This is a mathematical relationship which actually signifies this convex membership function. So if you take these 2 points, any 2 points, x1 and x2 in this range, and if you try to find a point, this point lambda x1, and you take one value lambda, and you try to compute this particular function, that will be a point, right? That point's membership has to be greater than or equal to the minimum of these 2 memberships. Okay, it's similar to the definition of convex regions if you have studied in geometry. Have you studied convex regions? Okay.
Ma'am, for the graph on the right, which is just increasing and never decreasing, is that convex?
Yes, it is convex.
Okay.
Increasing graph or decreasing graph. Only thing is if there's a dip like this, if this one, then it is non-convex. Okay. So what we can do is, I will talk more about this a little later. Okay. Because I want to prove this using these values. You can also try it. You can try it at home. You take these 2 values, any 2 values, take some example and see what you're getting. This relationship will not hold for this graph. This particular relationship will not hold for this graph. So it's better to simulate it through a program. So I will just show it maybe in a lab session by simulating it through a program. Okay. So there is one more alternate definition for the same. It is convex if all the alpha level sets are convex. Okay. So what are alpha level sets? Greater than or equal to that membership value. If all of them are convex, then fuzzy set is convex. Okay, we'll come to that again. I'll revise that again. But let me complete the other definitions quickly. So this is fuzzy number. Fuzzy number is nothing but a fuzzy set in the real line, which satisfies the conditions for normality and convexity. So a fuzzy number is a fuzzy set which is defined over a continuous discourse, universe of discourse, which is convex and normal. What is convex fuzzy set? Convex fuzzy set is that which, if it is having a dip, then it is non-convex. It should not have any dips. Dip and rise it should not have. Okay. And what is normal? Highest membership value is 1. The peak is 1. Okay. So fuzzy number means a normal and convex fuzzy set defined over continuous discourse, universe of discourse. That is called as a fuzzy number. That fuzzy set has another term called as a fuzzy number. Okay. Next is bandwidth. Bandwidth of normal and convex fuzzy sets. So the bandwidth of a normal and convex fuzzy set is equal to x2 minus x1, where the membership of x1 and x2 is equal to 0.5. So what is the meaning of that? What are these points? X1 and x2. These are the crossover points. X1 and x2 are the crossover points. X1 and x2 are the crossover points for the fuzzy set. Okay. So width is defined as for a normal and convex fuzzy set, where it is the difference, absolute difference between those 2 points. Which points? Crossover points. The membership is 0.5. That is the definition of a bandwidth or width. Next is symmetry. A fuzzy set is symmetric if its membership function is symmetric around a certain point x equal to c. If membership c plus x is the same as c minus x for all the x belonging to capital X. So that is very easy, right? Symmetric. So something like this. Okay. So this C which is there on the left hand side also. Uh, so, so this is say the center, right? So left hand side and right hand side, the landscape is the same. Then in that case, the fuzzy set is symmetric. It is said to be symmetric. That's it. Membership values will be the same. It is not like that here there are more values. And this lobe is larger and this is narrower around this point. Then this is not symmetric. Okay. So that is symmetry. Next is open left, open right, and closed. So open left, open right, and closed. So this is open left. So this is a open left fuzzy set. So if towards, as x is tending towards infinity, minus infinity, towards the negative values, it's going towards the negative values, then the membership is, the limit of that membership is equal to 1. And towards the positive values, it is going, the limit is going to 0. If the limit is 0, towards, as x is tending to positive infinity, then it is said to be open left. That is fuzzy set Young, open left, right? Similarly, what is open right? Same definition, the reverse the conditions, right? Open right will be limit as x tends to minus infinity will be 0, right? And as it is tending to plus infinity, it is 1. So what is that? For this particular example, young, old. It will be old. Fuzzy set old is an open right fuzzy set. Okay. So it will, as it is increasing, it will increase and it will become 1 finally. That is open right. Then you have closed MF. What will be closed MF with the same terminology?
Middle age.
Middle age. Okay. So as you're going towards both negative as well as positive values of x, you are tending towards 0. The membership is going towards 0. So that is a closed MF. So these are some more terminologies. Okay. We will stop here and we will discuss the membership functions in the next lecture. Okay. We will also look at this. Maybe I'll just give you a simulation of this convex fuzzy set so that you understand it properly with some values. Okay. We'll discuss that.